So we've got a lot to cover. I've got a lot of slides. We're going to be moving pretty fast, but I'm James Munns, and I talk about Rust a lot. So I work at a company called Fair Systems, and we do a lot of Rust programming. We do everything from embedded systems to back-end systems to robots to connected wireless devices to a lot of trainings. Ernest mentioned the trainings that Ferris has given in the past. But in general, we're a company that's really interested and invested in bringing Rust into the industry. So we're at a C++ conference, but as it was said, our hosts have been kind enough to share the stage with some folks from Rust. So I definitely wanted to share a little bit about the history of where Rust has come from, where it's going, and the kind of interesting things that have helped get it there along the way. So I think that Rust is a particularly interesting language. So I think working at a company that does Rust and coming here and talking about Rust probably speaks to my interest in and the kind of things that I find interesting about Rust. But I think there's a couple things that make it particularly interesting, especially for folks who come from different language backgrounds, whether that's a different systems language or even other language backgrounds like JavaScript or Python or Ruby or places like that. So I think that Rust is a language that is going places. It's not necessarily a language that has a 20, 30-year history like C or C++ may have, at least not yet. But I think Rust is a language that is particularly suited to take it to a lot of places, some of it that it's already started dipping its toes into, and some of it that I think it has a big potential in front of it for. So to understand where Rust is now and where it came from, I think it's important to look back at the history of Rust from the very beginning. And I promise I won't just say like the contents of the first paragraph if you read the Rust Wikipedia page, because I've given a couple of those presentations and I've seen a lot. So I'm going to take a slightly weirdly focused on a couple different times on the timeline of Rust. So if we go all the way back to the before times in the long, long ago, and when I say in the long, long ago, I'm talking about 2010, which 2019 already feels like forever ago. So 2010 has to be the long, long ago. So we want to zoom back to Mozilla in 2010. So in 2010, Firefox, as it still mostly is today, Firefox was written in C++. Now, if we remember an important fact around 2010 is that this is before C++ 11, which is definitely the before times. So there were certainly some problems with developing something as big and as complex as Firefox in a language like C++, particularly the pre-2011, 14, 17 versions of C++. The Firefox team, despite their best engineering practices, all the static analysis that they used, the code review that they used, and just the general organizational knowledge of shipping a stable product for years and years and years, when you hit a certain scale of complexity, it's just difficult to keep everything in line. And you start running into some real challenges, whether that's stability of the browser or ability to get rid of vulnerabilities and things like that. But there was something going on inside of Mozilla at the time. There was an engineer at Mozilla who had a side project that was a programming language, and he said, I think this might be a thing, and kind of pitched it to folks at Mozilla. And they were really looking at how they can leverage things that were changing about the ecosystem of people using Firefox. Processors were getting more and more cores. Resources were getting bigger, and it had become challenging to really leverage those in an effective way, particularly without running into more and more of those seg faults, memory safety bugs, or even just predictability of the system that they were working on. So when an engineer came and said, I think I can solve that problem, they were pretty interested to hear more about that. It was very early days. It was very much one person's side project programming language. And there's probably a lot of people here who have prototyped a programming language or played around with a programming language that wasn't ready to use an industry programming language. So they have a lot of hopes and dreams and ideas, but there's still a lot of problems to sort out. But Rust, even in those days, still seemed sort of promising. Rust as a language, even then, had an eye on concurrency. How can we make it just as easy to leverage 2, 4, 8, 16 CPUs as it is to leverage one? And what if that didn't make things harder to manage? What if that instead just made your code run faster? So now we've fast forwarded a year forward into the year 2011, which is still the long ago. But at this point, Mozilla had said, we'd like to take this from a hobby project of one of our engineers to something that Mozilla is willing to research on. So at this point, this is where Mozilla was starting to introduce Rust inside of Mozilla. It went from being a sort of one person or really skunk work teams to a specific focus of the Mozilla engineering organization. So these are quotes from the slide at the Rust All Hands in winter 2011. So this was a Mozilla event in 2011 where Patrick Walton was kind of bringing the Rust programming language and introducing the Rust programming language to other folks at Mozilla. They introduced Rust as a new systems programming language designed for safety, concurrency, and speed. Those were the taglines then in 2011, and folks who have followed Rust since then probably recognize those as kind of the big marketing material of the programming language itself. Even at the time in 2011, Patrick introduced Rust as a language that was originally conceived by Graydon and is now developed by a team at Mozilla Research and the community. And this is one of those things that was a common running theme, is even from day one, there was an emphasis on the people in the community who were interested in contributing towards this project while having a dedicated project within Mozilla to really bring this language to completion. So at the time, they weren't just saying, let's build a programming language. They said, we really need, as a company, to have a focus piece. What is our unique, what is our minimum viable product, or what's our unique selling perspective? And Patrick described the Rust project as a critical piece of the Servo project, which was essentially a test bench or research platform to develop a parallel first browser engine. So rather than a browser engine that has a legacy of 10 or 20 or 30 years of history of where it came from, so probably growing organically from a single core model to a multi-core model, what if we designed a browser engine to be parallel from day one? Even then, they said, we don't know how or whether we will ship this engine to users. Nevertheless, this is our research platform, and whatever we build on this research platform, we want to be at a production level of quality, because they said, if we're going to really take this seriously, it has to be something that at some point we'd be comfortable hitting the merge button onto either Firefox itself or to a new browser that could replace Firefox potentially. So Rust at this point went through a really huge stage of explosion and contraction. So we're talking about feature explosion and feature contraction. So in that time between 2011, when Mozilla put some serious engineering resources and some serious community resources behind Rust, to when they shipped the first version of Rust in 2015, there was a big cycle of changes in there. Rust spent those 4 years taking inspiration from many places, and a lot of this has a flavor of the people who were working on Rust at the time, whether that was people inside of Mozilla or people outside of Mozilla. We had a wave of people from the Ruby community, the Haskell community, the C and C++ communities, the ERLANG community, who left their stamp on the language. So if you look at a snapshot of Rust between 2011 and 2015, it was like 12 different languages in that time. And there was kind of this constant churn of figuring out what makes sense for Rust in the long term. So a little bit of this was research where people would say, I have an idea, and they would throw it out in IRC in the morning, and they'd merge a PR that broke everything by the end of the day. So it was really based on the interests and the research aims of this team. During this time, you probably wouldn't recognize a lot of Rust. And Rust, in those 4 years, threw away a lot of features that some language don't even have. In that time, there's a really wonderful talk by Marin at RustFest in 2016, where he goes over the Rust that could have been. And he focuses on a couple of these weird things that Rust threw away. Things that are maybe commonplace for other languages, like green threads, which might be native to Go or Erlang kind of developers, or garbage collection, which might be familiar to JavaScript or ERLANG or Python developers, or type states, which might be more familiar to people who write in languages like Coq or other proof-based languages, and even more. There was weird syntax, there was weird features, there were things where someone goes, if we could get this to work, it'd be really great, but it sort of works today. So over those 4 years, there's this big run up and rundown and churn where you really couldn't expect stability from Rust the language or Rust the compiler. Sometimes Rust broke everything on purpose because they said, we think this is the way forward. And sometimes it just broke because someone merged something and there wasn't, always this production user focus on a day-to-day basis. It was definitely the long-term focus, but it wasn't necessarily what people were doing day-to-day. Shortly before 2015, that perspective changed. It was time to get serious, and they realized they were getting close to Rust 1.0. I think at this time, this was Rust 0.9 or 0.11 or 0.13. But essentially, there was a shift that says, hey, in the next couple months, we're going to make a 1.0 release. So we need to start thinking about what we're keeping and what we're throwing away and tackling some of those problems where we went, we'll have to tackle that someday. They said, well, 2015, Rust 1.0, we got to either tackle it or pitch it before then. So it was time to cut a stable release. Around the run-up through 2015, Rust said, we are going to ship a stable version of the compiler. And perhaps some of this was just compensating for the last 4 years of churn, but they went, we want a language that people can rely on and can trust in. We want people to be able to write software in Rust, and it should work for as long as the Semver version of Rust. So Rust 1.0 should always work with Rust 1.x. So they kind of drew this line in the sand before this 1.0 release happened, and they said, this is our plan, and we're sticking to it. So over this time, over the whole course of the 4 years, the how changed. How the language achieved this safety and concurrency and performance changed a lot. It went from being a language like Erlang or Go in terms of, well, we'll be safe by being garbage collected and having green threads built into the language so you can do concurrency, to over time looking like a language a lot more like C or C++, but with a lot of these features that you'd expect from other languages like Erlang or Haskell or Ruby or Python. But at the end of the day, they were still aiming for this safe, concurrent, and fast kind of operating environment that's really necessary for a browser, but also really useful for a lot of different domains. So now we're starting to get to the post 1.0 days in 2015 to 2021, which is the Rust that most of us kind of know and love at this point. So I'm going to take a quick look at the Q&A, and I want to give a quick reminder. So I don't see anything in the Q&A, but I am going to take a couple breaks every now and then. I think I've got 4 or 5 stop points in my talk. So if you have any questions for what I'm doing along the way, or just things you'd like to know more about, feel free to throw those into Q&A, and I'll keep an eye on those in my stop points. And definitely, if I don't have time to talk about it during the talk, I'll come back and sit down with folks in the general chat and talk about it after my talk. So now we're talking about Rust, the stable language. Rust that shipped in 2015 and has been delivering a new version of the compiler, a new stable version of the compiler every 6 weeks since 2015. And now we're on Rust 1.46 or Rust 1.47. You can go to whatrustit.com and you can see what the current, the next, and the following versions of Rust are going to be. But it's shipped like clockwork every 6 weeks. So it turns out that even though they made this commitment to stability, Rust never stopped being a language that changes. Rust is a language that keeps shipping new things, and when people improve things, or whether that's an incremental feature or a drastic feature or something in between, Rust has always had this culture of continuous change. The language makes stability guarantees, but you always can expect new things from Rust. And you shouldn't expect a language that's set in stone. You should expect a language that evolves in a pragmatic and usable kind of way. And that stability guarantee holds. You can still run and compile code that was written on November 2015 or whatever the release date was. You could ship that with today's stable compiler, and it is going to compile and it is going to run no problem. There have been no breaking changes, asterisk, in Rust. So I put a little asterisk, and I promise that asterisk isn't as bad as it sounds. There's kind of one escape hatch here, is that if there is ever a soundness problem in the language, Rust has said, just because we shipped it doesn't mean we're going to codify that in stone and work on it forever. If that's something that shouldn't have worked with Rust, whether that means you can evade some of the static analysis or evade the borrow checker or the type system, they'll consider that an oops, and they'll fix that. But there's been a big focus on minimizing those. So if it was just something that it was, oh, hey, we didn't clarify whether it was A or B, it's going to stay in the language. But if it was very clearly, oops, I can corrupt memory using this feature from Rust 1.2, we're going to fix that. So Rust tries to think about trade-offs differently. Instead of the very engineering, no such thing as a free lunch, we think about reformulating the actual problem and figuring out the things that people really need and what they're okay with not thinking about, or how can we get safety and concurrency and stability pick 3. Or you'll see this a lot in marketing material, or people use this tongue-in-cheek in their projects where they say you can have A or B or C, pick 3. And that's kind of an emphasis on the approach to solving problems in Rust is, can we think about how to solve this in a new way that makes this work for everyone, or at least for most people? So we also think that systems programmers can have nice things. Just because you work in a compiled language that's going to run on a microcontroller that only has 2 kilobytes of RAM, or a WASM runtime that's going to run on the browser, which may have limited resources, that doesn't mean you have to throw everything away. You can move some of that checking and convenience to compile time, so your runtime system, even though it's only got 2 kilobytes of memory, still has an amazingly expressive type system or a package manager that works with you. Or if you have to fit something that has really crazy performance because you're doing it billions of times a second, that doesn't mean that you can't write really expressive code with iterators and things like this. And these are concepts that are not new to Rust. C++ has been talking about zero-cost abstraction, or the core guidelines, or doing things in the new ways and not making them painful to do. These are kind of the songs that C++ have been singing for a very long time, but Rust has kind of made this an integral part of the language culture. So remember when I said that there are no breaking changes? Turns out that was a lie. And Rust has taken another one of these, how can we solve this problem in a different way kind of approaches too. Well, Rust has these things called additions, which are sort of like C++ 14, 17, 11, where we introduce new stuff. But we realize that the thing that people don't really like about breaking changes is they have to touch their old code. They have to rewrite some old code that's working today, but just for the sake of being able to use the new good stuff, they have to go back and do the maintenance burden on the old stuff. Well, Rust kind of went, well, we have packages or libraries or crates. What if you could just say that old crate uses the 2015 version of Rust, and this new version of, or this new crate that I'm writing today, where I want to use the new flashy features, maybe that one's 2018. And what if they just work together seamlessly and people didn't have to touch the old code that's just working, but they get to use the new features on the new library or the new application that they're using? So sort of without telling anyone, we sort of maybe shipped Rust 2.0, and it wasn't a newsworthy event because it didn't break anything for anyone and no one really noticed. And sort of a spoiler, we're about to have the 2021 edition of Rust, where we're about to have, don't tell anyone, Rust 3.0. And I think it's going to be just as unmemorable as Rust 2015 or Rust 2018 or Rust 2021. And I think that's a pretty beautiful thing, because that's what people want. They want to be able to write their new stuff using the new functionality and capabilities that are available to us, but they don't want to break something that's not or they don't want to change something that's not broken just for the sake of change. Rust also looks at these trade-offs in a sort of different way, where things like safety shouldn't be optional. We had a chat with the C++ folks last week on the CPP Chat podcast, and it's interesting to hear that you hear people who have worked in industry pragmatically. They say, when you are developing C or C++, you should have all of these warnings on, and you should use these tools configured like this with these kind of static analysis, always on, no exceptions. But when you're starting to use the language, you just open up a compiler and you start writing code and you copy and paste some stuff. What if from day one, safety wasn't optional, and it wasn't you have to opt into safety, instead you have to opt out? Well, Rust has made those kind of trade-offs at the language level, where we take things like memory safety or concurrency safety very seriously. And while we still give some escape hatches for folks who are promising that they know exactly what they're doing, with keywords like unsafe, we make the default safety. And this is one of those things that has had a really big impactful change, because you find out that people do the thing, they do the default most of the time. And if the default is safe, then most people will use that most of the time. And if you have to drop into the other options, you still have those options. And it turns out not just that people do that by default, it turns out people really like that. They end up writing code that doesn't break for them in surprising and interesting new ways. Or when I say interesting new ways, I mean ways that you find out when you only have 1 million production users at 4 a.m. while your entire dev team is sleeping. And that's a really cool thing, because people come away with this really positive view of Rust because it's never bitten them before, or it very rarely it bites them, or it bites them up front and they can plan for that. And once you ship it, it just kind of keeps doing what you asked it to do. And it seems like in practice, from all the things that I've seen from when I was a hobbyist in Rust to now as a consultant and a trainer, people who are interested in Rust or people who have worked with Rust in the past, people just get this odd affinity to Rust. And once they start using it, and once they learn how to use it and start using it in projects, they like to keep using it. And that's one of those things where, for someone who's used Rust, they go, oh yeah, that makes sense. But if you haven't used Rust, or if you haven't played around with Rust, you're left saying, but why? It's just a programming language. Why would I go through the hassle of learning something new just to write something that I can say, oh, well, if I only use C++ 11 or 14 or 17, I get all the good stuff, right? I don't have to worry about learning some new language, and it works with all the code that I've been writing for the last 5 or 10 years. Well, it turns out there are a lot of reasons why, and I'd like to go over a couple of them. I'm going to peek into the Q&A. So before I get into what I want to see, I want to go through a couple questions. What breaking change would I like to see in Rust? That's a much longer question, so I'm going to save that one for general chat, but I would like to answer that. Why is it called Rust if it's always fresh? Because it's named after a fungus. How does Rust handle ABI stability? It doesn't. There is no ABI stability, except for you can opt into the C ABI, and Rust has just said, no, we're not going to stabilize that. That's also something I'd like to talk about. What's the speed of Rust compared to C++? I'd probably say between C and C++. Benchmarks are weird. It really depends on your use case and the code you write and how idiomatic it is. But generally, you can see Rust floating between C and C++ depending on what you're doing and how well optimizers pick up on it and what your actual use case is. Is there a checklist when thinking, should we rewrite X from Y in Rust? Yes, and I'll get to that later. Okay, I haven't gotten more upvotes on that, so that was my lightning round. So please keep asking questions, and I'm happy to come back to these later. Still doing good on time budget. Cool. So I think there's a lot of reasons why you might like Rust, or why I like Rust, but these are a few of my favorite things. So I think Rust as a language has had the chance to be sort of a greenfield development, and not just from a programming language perspective, but also from a community and mindset perspective. Rust, the people that I find that have worked on Rust all generally agree that computers are hard and that there is no need for people to make that worse. We're all kind of on the same boat of having to work with computers, and as powerful as they are, they can be really sort of interesting sometimes. And we don't have to make our lives any more interesting because boring is good. And sort of the experience that I've had from working in embedded systems or system programming, whether you're talking about an operating system or a database or a file system, is you see a lot of stuff over the last 20 years that was, yeah, that's just bad. You get over it eventually. Or, oh, you didn't read that book. That explains to you how you avoid all the stuff. You should just read that book. Or, I went through it and it was awful. So it's character building. So you should do it too. And you'll learn why all those things are important. And we deal with sharp tools that cut deep and it's important for power. And, I don't see this so often in the Rust community. I see a kind of a mindset that reminds me of the favorite teams that I've had working on in my experience in industry. The kind of teams where you go, when someone runs into something painful, they figure out why it was painful and they fix the problem so no one ever has to suffer the same pains. That could mean building bridges for people new to the language or the concept so they don't bump into that concept that people obviously are going to bump into, or just figuring out how we can solve this once and for all, where we say, yeah, instead of just file systems being awful, what if we just figured out a way to make a fairly reasonable interface over that and let people opt into the awful interface if they really need it? And instead of putting all of the responsibility of getting things right on the people with a kind of a mindset like, we're real programmers here, and if it's hard, and if you don't understand it, you must be not smart enough. I don't know why I dropped into an accent like that. Maybe, I don't know. It probably says something about my psyche. But instead, taking a different approach, that if something is unclear, maybe that's a bug in the tool, or the documentation, or the library, or the compiler, or the test suite. And maybe we should treat that like a bug, and maybe we should fix that. Because instead of putting that onus on every single one of the contributors that uses this tool, why don't we just fix it? And I think this sort of comes from a very open source and collaborative mindset that Rust comes from, is that Rust was weird when it started, and there's only so much weird budget you have to spend and still expect people to keep showing up and contributing code and trying things out. So, you pay down some of that debt in documentation or, tooling and workflow, so they keep sticking around for when you had the @ symbol, which meant a garbage collected reference pointer or something like that, whatever it was in 2013. Rust has also been a language that is willing to steal from anyone with good ideas. There's no point where we say, we're a systems language, we can't have heap allocations or vtables or exceptions or whatever. We go, hey, if someone else figured out something, there must be something to it. Even if we can't do it exactly the same way that they do it, there's something to it. Whether that's someone like JavaScript or Ruby, who, when you compare it with something like C or C++, you look at a language like JavaScript and Ruby and you go, compared to C or C++, especially in 2015, they have package management way more figured out than the average C or C++ project. So let's steal that from them. And the stealing wasn't really so active. A lot of the times it was just people coming from Ruby or JavaScript and said, wow, yeah, I miss NPM or I miss bundler comparatively to like CMake, for example. So let's build one of those that works for Rust, and let's do that. And people came from C and C++ and they said, I like fast code, and I like the ability to really customize things the way that I need when I need it, because I work on embedded systems or databases or operating systems. And they go, well, we need that too. Or I want to be able to choose whether I'm spinning up 1,000 threads or 100,000 workers on 100 threads. Or I want processes to be able to fail, and I want to be able to recover from that. And people from the ERLANG background went, yeah, maybe we could do that in Rust too. How would I do that nice thing from somewhere else? How would I bring it here? And I think there's something really important to that, of people bringing the things that they like and figuring out how to make this fit into the big picture of this language that we're all working on. So there are things, I'm going to run through these real quick because I could go on for days about this. So I'm going to give you kind of like the tool and why I think it's not just a tool, but you can kind of get the flavor of Rust from it. So we have a package manager. We have Cargo that was inspired by Bundler and NPM, but it shows that Rust as a language thinks about sharing from day one, whether that's sharing libraries or sharing tools. And it means that people are in the mindset of, solving a problem and sharing their solution. Cargo is also a really good use case of it doesn't solve all of the problems. I know folks at like Microsoft and Facebook and Google, they don't use Cargo because they have their own in-house, very specific to their workflows kind of thing. But for like 98% of people, Cargo is the package manager in the build system that they want. So maybe provide good tools that begin with and leave escape hatches for the people who say, I need to do ridiculous thing for a very good reason, but still compared to the other 98% of the population, very ridiculous. Rust has a crate or a library repository like NPM or Ruby gems or things like that. We have a package manager called crates.io, and it kind of becomes the one place where you go, I want to use something from somewhere else. I'm going to go look at crates.io. And thinking about sharing of, I should probably think about, I'm going to publish this. Maybe I should, write some documentation or tell other people that I've written some solution to some kind of problem so that other people can use it. And maybe make it easy to share these solutions with everyone. Rust came with not just a build system and a package manager built into Cargo, but a tool called Cargo Doc. If you've used Doxygen or Read the Docs or Sphinx in different languages, it's sort of like that, but it's built into the build system. And it comes with basically a standard interface that we use for the standard library documentation, as well as essentially every published crate out there, which means everyone has a good example to go to where they say, how do I write good docs? Oh, I'll go look at the standard library. I'll write docs like that for my own package. And when you submit your library to the package repository, there's a website called docs.rs that goes and uses that tool and publishes it publicly. So even if you haven't pulled down that library, there's one repository of essentially every open source Rust tool or library that you can just go searching through, and it's consistent with everything you've used. Rust came out of the box with something called the book, and it's the Rust programming language, which was a totally open source CC by shared attribution reference guide of how to learn Rust, a really print quality book. And when I say print quality book, I mean people have printed this book and you can go to the shelf and buy it, but you can also just go to the website where it's hosted and you can see all of this as it changes, and people are updating it continuously. And this sort of like set a good example for the community, because now when people write big libraries, instead of being like, it's a big complex framework and just copy and paste some repos because no one really actually understand how it works, people think about writing books for their own projects as well, because they understand, sometimes things are hard to learn. And if we write documentation and people can learn how to use it, and I provide examples and I provide how to use it or why or when you might want to use it, I'll just do that for my project too. And it really builds this culture of documentation when it's so easy to do it and when it's so expected of the community to do this. Rust is a strict language. I said that it focuses on safety by default, and that means the compiler is really mean. It takes perhaps longer to get something working, but I'd say it generally takes less time to get the right thing working. And this is something that some people struggle with, but people sort of really like about Rust is it tells you immediately when you have messed up, and it is very unforgiving. There's no, just let me just ship this. It's just like, no, does not compile, sorry. And it turns out some people like that feedback. But the flip side of that is, the Rust compiler has some of the best signal-to-noise ratio of any error or warnings that I've ever seen, and some of the best diagnostics that I've ever seen. And Esteban Kuber, who's kind of one of the people who's really pushed to improve diagnostics in the Rust language, he has this saying that I really like, is that there are no bad programmers. There's just insufficiently advanced compilers. Because he says that if a compiler can just compile good code, it's not a very useful compiler. The compiler has to understand the terrible wrong code that you've given it, either because you made a mistake or you're a brand new learner and you don't really understand what syntax goes where. The compiler should not just understand Rust, the programming language. It should understand Rust, the programming language that people are trying to use, so it can guide you into the right kind of solution. And this is kind of that mindset of build bridges, don't gatekeep. And I really like that in the Rust community. Tooling, again, building bridges. People build tools, they share it with other people. I'm running behind in my timing, so I'll keep going. But there's a big culture of writing tools and publishing them and making them easy to use in the Rust community. People just share stuff, and it's pretty cool. And that community that I keep going back to is really what I think the special thing about Rust is, because you can have a programming language that is a technical marvel, but that's not going to make people use it. And you can have, the highest performance, and you can have the best benchmarks, and you can have the best standard library, but if people aren't going to show up to use your programming language and improve your programming language isn't going to go anywhere. People are going to use it for the one thing that they really think they want to use it, and they just kind of use it like it was a hammer. But when you build an environment where people feel welcome, where they say, I can make an impact here, and I feel welcome here, and I like the other people who are here, they stick around. They take all those experiences that they had from learning Ruby and learning JavaScript and learning ERLANG, and they take all those experiences that they learned somewhere else, and they go, well, I liked those things, but I like hanging out with the Rust people. So maybe I could just take all the really good stuff that I liked about that other language, and maybe I could just do it here too. And Rust has had waves of this from a lot of different people coming from a lot of different backgrounds, from new programmers to seasoned compiler developers to crusty embedded developers to people on the forefront of every kind of technology. And people just go, it's nice here. I'm just going to bring the stuff that I like and all these lessons that I've learned from one day or 1 year or 1 decade or a whole career of learning. And maybe I'll just make the Rust area better because other people are doing that too. And I kind of like hanging out there. So Rust aims to be a language that empowers everyone to build reliable and efficient software. Doesn't matter if you've never programmed anything before. We think you should be able to program an embedded system, or you should be able to program an operating system. Maybe not today, but you can do it. So I'll go back to questions before I go on to where I think next is going to go. How does Rust handle multiple editions with a single runtime? Basically, the compiler understands how to translate between the different versions and then kind of makes it all coherent on the back end. Certainly, when we have 27 versions of Rust, this may not be totally great to do. But right now, where we have 2 going on 3, and that's good for another couple years, it's a reasonable solution for now. Standardized async runtime. I am not the right person to talk about async, so I will avoid that question and give you my best guess in the chat later. Async, there's some people at Ferris who know async, and I am not one of them. I think it's really cool, but not my area of expertise. Who decides the Rust language evolution? There's an open source kind of working, or there's the core team. Well, I'll get into governance. Let me talk about that in chat. Essentially, it's all open source. There's a process called RFCs where people propose new changes to the languages or the libraries, and people talk about whether it's a good idea or whether a bad idea or what implications we have or how we can make it better. Yeah, I'll leave it at that, and I'll answer more detail later. I think there's the same questions as there. Yeah. Okay, cool. So let's keep going before I run too bad on time. So I think Rust even has the possibility to walk into new arenas. It's already made some marks on things like backend systems. All those company logos that you saw in the slide from Ernest, people are using Rust there, whether it's backend services or cryptography or cryptocurrencies or embedded systems or front-end development. People are already using Rust, but where could Rust move into that might be particularly interesting? Well, WASM's a particularly interesting area because it sort of came around after Rust. So it's actually sort of a thing that's newer than Rust. And it's kind of interesting to see Rust as a language that started as a language for browsers. And now Rust and WASM sort of are friends for the front end and outside of the front end. It's interesting to see that come full circle. But where can we use Rust in the context of WASM? So what WASM is, I think there's a talk later today that's going to talk a lot more than I am qualified to talk about WASM. But WASM is generally WebAssembly. And what it is it's a binary representation of a programming language that can be used in a variety of different contexts. So either in a browser, as instead of interpreting and running JavaScript, having a somewhat different representation on the wire that you can use many different source languages to compile into a WASM kind of environment, or It's kind of an operating environment where you can do things like have strongly containerized or semi-containerized or isolated processes that are, separate from each other in the same way that you would like a browser to be keeping all of those different websites that are running code on your computer to be separate. And I'll leave it at that. But there's kind of two aspects where Rust has found a home in WASM. And one is in the WASM Runtimes. So this is something sort of like an interpreter or something like the JVM, or I'm probably murdering this and there's WASM people who are very upset at me, but this is the engine behind the scenes that takes that WASM and turns it into operating code. And this is something that is expected to be very performant and very reliable and very safe because it's responsible of keeping all of these different applications separate from each other and well-behaved and running smoothly. So you could think of that sort of like a browser. So I guess it sort of makes sense that people are using Rust. But of the major WASM runtimes that exist out there, and there's quite a few, Rust is prominently featured in most of the large ones, either as a part of the runtime or as the entire runtime implementation language. And for these runtimes, safety and performance are paramount. Like I said, you want to keep things separate so you can keep your data safe, but you're running code and you want it to be as efficient as possible. But people aren't just using Rust to build the engine that drives WASM. They're writing code that gets compiled into WASM from Rust. And this seems kind of interesting because you go, well, it's a language for running on a browser front end or in a very limited environment. Why would I use Rust for that? Why wouldn't I use some higher level language or different language that can be abstracted down? And there's a lot of reasons for that. And on one hand, Rust allows you that performance and control because Rust is a language that doesn't have a runtime. There's an asterisk there, but has the same amount of runtime as a C or C++ style language, which means you can still control all the stuff you want to do. And for people who are coming from JavaScript, but they want, more control or more performance out of their website, this really sings to them. And it turns out that it works just as well for WASM as it does for embedded systems. And it turns out all that emphasis on tooling that people have been doing in Rust kind of shakes out in WASM. In the early days of WASM, there was, a lot of duct tape and glue that was required to get things up and going. And there's still a little bit of duct tape and glue required, but it's becoming less and less year over year. But when people said, well, I'm doing this new researchy thing and I need to build some duct tape and glue, what am I going to build it in? People went, well, I'm already building tools in Rust, so let's just build the WASM tooling in Rust. And this spawned a lot of really cool projects like WASM Pack and a number of other tools that made Rust the easiest language to build WebAssembly code in. WASM was also, going back to that community thing, WASM was the first taste of a systems programming language for a lot of people. These were people who were interested in the JavaScript kind of world, but they wanted their website to run faster. Maybe they were generating images or doing graphics and things like that, and they wanted more control and more performance, but they've only programmed in JavaScript before. So where are they going to feel comfortable coming from a JavaScript background, but learning a systems programming language? And it turns out Rust was a welcoming community for a lot of those folks. And Rust already had a lot of people who had been using JavaScript or Ruby or Python in the past. So, they called their friends and they came to join the Rust party in a lot of places. So embedded is sort of my background and experience and workhorse. I really like playing with things that interact with the real world, whether that's blinking lights or moving motors or having airplanes talk to each other from 100 miles away. Embedded is a really interesting application because they're just tiny little systems. They've got kilobytes of RAM and they've got little single or double-digit megahertz CPU, which means everything's sort of a challenge and everything's super bespoke because you're trying to pack all that functionality into the smallest and cheapest package possible. And it turns out that if you kind of look at it weird, embedded and WASM are actually really similar because you've got a limited operating environment, you got to go fast or you got to go efficient, and you've got to, think about the kind of things that you're doing. And I think personally, embedded has been unnecessarily hard for a really long time. It's been one of those industries where people say, we've always done it this way, or yeah, it's hard. You got to sign 6 NDAs with a vendor and they send you a CD with a compiler that was compiled 16 years ago and it's based on GCC2. And you go, that's how you develop embedded systems. And it's hard like that because it's hard like that. And open source software development has changed a lot of that. And Rust's ability to write tooling or write powerful abstractions has made it so you can actually just not do that, because it turns out that's not a mandatory part of the experience. It's just what people kept subjecting themselves to, or their vendors kept subjecting them to year over year. And Rust has had stable embedded support since 2018. That was one of the big pushes, where on day one, we didn't have embedded support because those weren't the first people there working on the compiler. But we always kind of said, if we could do embedded, we'd like to do that too. And around 2017 is when a couple of us got together and we went, let's do it this year. Let's make 2018 the year that we have stable embedded Rust, because I really want to start using this for production projects. So since then, we've been pushing Rust lower and lower and lower into lower power systems, and being able to work on those systems more and more. And it turns out Rust goes back to that not having to make trade-offs, because it turns out even though you've got this tiny little system with 2K of RAM, your development system has 64 gigs of RAM, and you've got a 16-core processor. And it turns out you can make the compiler work really hard to make sure that your embedded system is going to work right at runtime. And once your compilers thought about it and said, yep, I'll sign off on that, that's good, that's going to be safe, turns out then your microcontroller doesn't have to check all those things. It doesn't have to check null pointers every time you pass a pointer into a function. And it turns out you don't have to check whether you've already configured the UART, because the compiler can say, oh, yep, you've only configured that hardware once. Or you don't have to think about, how do I handle like writing my own vtables because I want portable code, but reusing code means copy and pasting code from one project to another. It means that you can use all the fun functionality of Rust, whether that's generics or monomorphized code or traits or dynamic dispatch or compile time macros or AST macros. Turns out all that stuff that just lives at compile time, your microcontroller never has to think about it. And it helps you write embedded code that can't go wrong, at least for a subset of things that could go wrong, because you've checked it at compile time. And if you know that it works then, why check it at runtime? And we can leverage a lot of tools. People like building tools in Rust. So we've already started building things that have been historically painful for embedded developers. So if you say the phrase OpenOCD to embedded developers, they go, yeah. And OpenOCD is a very powerful tool that has had a very long lifetime and has been very cool because it lets you develop software for a lot of different microcontrollers across a lot of different platforms. And it's one of the first and best open source tools that help you develop code for a microcontroller. But it's a little long in the tooth, and its development cycle is sort of weird, where I think it's still based on SourceForge, and they haven't had a release in like 5 years. So there's just like some bespoke branch that someone has in a fork somewhere that everyone sort of uses and distributes, but it's just not great to work with. And the scripting language is Tickle, and I never really learned Tickle. But it's one of those things that everyone uses, and everyone goes, yeah, I don't really know how to use it, and it's kind of painful to use sometimes. So as Rust developers, we went, what if it wasn't bad? What if we wrote a new one called probe.rs that uses Rust, and you could use it as a library, or you could use it as a command line tool, and when you just run cargo flash from the command line, it will just figure out what you want me to do and flash your microcontroller, and if I'm not sure, I'll ask you. So people have been fighting with tools to make things more palatable in these industries as well. At Ferris Systems, we've been working on that too. We've started this open source initiative called Knurling RS, and we love puns in the Rust community. But knurling is supposed to help you get a grip on bare metal Rust. And we've been kind of doing those same kind of things. We said, as people who are working in production on embedded Rust, what are the pains we've had, and how can we solve that for everyone else? So this is something that we've been really working with the community of solving the problems that we've had and taking feedback from the community to not make this a problem for anyone else. So I'll finally get back to one of my favorite workhorses, which is safety critical systems. I've worked in avionics, I've worked in robotics, I've worked in gas detection. I think safety critical systems are really fun software systems to work in. They come with a lot of baggage, though. There's a huge amount of regulatory overhead of people telling you what you can and can't use to develop software for an airplane or a car or things like that. And it comes from a good place. They want to make sure that the software you write is done well, and you're using good tools, and you're using tools that are just as good as your development practices and the code you write. But it means that there's a huge amount of development inertia because people are afraid of changing things, because every time they change things, there's a lot of paperwork. And they've always done it that way, and they know that if they do it the same way as the last project, the the people checking their work aren't going to be surprised by it. But that means that they're still using practices from 5, 10, 15 years ago, and they're sort of stuck in the Stone Age. And I think there's a huge potential for improvement because other areas like back-end development and front-end development have been learning over those 5, 10, or 15 years. They learned how we can develop reliable software faster and how we can put less emphasis on the old ways of testing or the old ways of verifying and come up with something that still meets those objectives, but, has a new spin to it. And I think Rust can really be a huge potential for improvement because most of these folks are using either C or C++, or in typically very old versions. It's not unusual to see C89 in these projects still. And that's a lot longer than my career. But yeah, I'll make sure I keep moving, but I think we can do better. So this is Sealed Rust, which is Ferris's effort to bring Rust to safety critical systems. We're working on a lot of things. This is worth a whole talk. I talked about it at Oxidized Conf, but I'll keep moving so I'm not crowding out the time. But I think Rust is well positioned for these industries, despite all the due diligence that's required. So where do we go here? There's still a lot of software out there that isn't Rust yet. Well, someone asked me, when should I rewrite in Rust? And I don't think Rust is ever going to be replacing all software. We're still writing COBOL today because that COBOL code works and it's worked for 50 years. So don't touch a working system, especially if you spent a lot of money on it and everyone from the team left and it works, but no one knows how it works. Don't rewrite that in Rust because that's going to go bad. Let that keep working and don't touch that. And while you can do a lot of things in Rust today, it's not always as easy as the tools that already exist. So there might be problems that are maybe better for other languages. And I think even Rust is willing to admit that in a lot of times. But I think Rust is a language that changes, and Rust is going to keep raising the bar on what is easy and what is possible, and whether you should do something in Rust or not, or whether you should pick Rust for your next project or not. And I think it's really saying that programming languages can't stay static anymore because they'll be left behind. And I think Rust is going to continue to be a good choice for new development. If you're not doing things the old way and you don't have a lot of legacy code, you probably should think about Rust for your next project. And even if you're just rewriting part of your next system, maybe you should think about Rust for that part of your system. And I just think that's neat. So thank you for listening to me talk about Rust and accessing all arenas. I'm James Munns from Ferris Systems, and I'm BitShiftMask on Twitter. And thank you all for listening to me talk for a very long time about a programming language. So back to you, Phil.
You've actually got a few more questions if you want to finish them up.
Sure. So please explain the meaning of knurling. I don't get the pun. Do I have something on my desk that is knurled? So have you ever had those little metal thumb screws that have those little diamond patterns on them? They look kind of like this, and they're just kind of like a texture that you put on a metal screw. That process is called knurling, and we call it the joke because it puts a better handle on bare metal. Yeah, the joke's that bad. It was like a 3-year-old joke, and we couldn't come up with a better name, but I actually sort of really like it. Any big project doing C++ and Rust interrupt? How painful or powerful is the native interface between such components? Yes. Firefox is doing a lot of that. There are a lot of tools like BindGen and CBindGen that make it easier to go one way or the other. It's not without problems because Rust as a language makes a certain set of preconceived notions, and C++ as a language makes a certain set of preconceived notions. And making them fit together means you have to think about both of those sets of preconceived notions and make sure that you never screw that up. So there are some tools that are making this easier with varying levels of overhead. Firefox has been doing this from day one of replacing components as you go, but also companies like Microsoft and Facebook are thinking about this too, because they have a lot of existing C++ code, but they would like to be writing a lot of new code in Rust. And that's just one of those things that Rust plays fairly well with the C, or plays really well with the C ABI, and people are thinking about how they can make interop with other languages like C++ or Swift or Kotlin or Python or Ruby even less painful. Can you see Rust being used to write an operating system? Rust has already been used to write a lot of operating systems. So there's a fairly full-scale desktop operating system called Redux OS, which is an alternative operating system that is aimed at the desktop environment. There's real-time operating systems like TalkOS or Arctic, which is sort of an operating system, sort of not. But there are a lot of other teaching operating systems like Intermezzos and Phil Opperman's Blog OS, where people are making varying levels of production quality operating systems in Rust already today. And there are already companies like, what are they called? Oxide Computers, who are writing their own operating system for using on parts of, for example, the motherboard for server computers and things like that. So we're already there, and we have been for a number of years. And that was even before Rust was stable for writing embedded systems or operating systems. But now it's stable, and there's people doing it in production today. So I think I've cleared out the backlog of questions. So thank you all for listening, and I'm happy to hop. I'm going to need to drink some liquid and not talk for a second, but then I'm happy to jump into chat, either general chat or one of the tables, and answer more questions. So thanks everyone for listening.